Well, thank you for having me. So I am Ayan. I recently graduated from Vanderbilt, where I did my PhD in the Computational Economics Research Lab on decision-making under uncertainty, and I focused a lot on AI for social good. I work heavily with the Institute of Software Integrated Systems, which is also at Vanderbilt, and is an acronym that spells out as ISIS. Imagine talking about your work at airports. And I am now currently working with Michael at the Stanford Intelligence Systems Lab, and I'm going to talk to you about intelligent emergency response. So before we actually get into the details, I'd like to motivate the problem a little and what got us into working in this field. So I have a few numbers for you, mostly through newspaper cuttings. This is one clipping that shows you that violent crime in the US has been rising. Okay, so it's not true for all consecutive years, but even in a country like US, we have observed that for specific pairs of years, violent crime has been on the rise, which is something which is really staggering. And it's not only the case with violent crimes, it's also with vehicle thefts as well as burglaries. If you can read the newspaper article, it actually says that the total amount of property losses just from burglaries every year, only in the US, amounts for about $5 billion. To give you the specific numbers, we have over 1 million violent crimes, over 8 million property crimes, and in comparison, only 900,000 law enforcement officials, which tells you that there's a gross mismatch in the total number of attackers, if you will, and the total number of defenders we have in this regard. Now, this is not the case only with crimes. It's also the case with motor vehicle accidents. This is a really old newspaper cutting from the 1930s, which tells you that the whole country was very concerned about the total number of deaths being caused by motor vehicle accidents. And it's been about 90 years from then, so you would imagine that the problem has been sorted, but it turns out that it hasn't been. This is a rather recent newspaper clipping, which tells you that on an average, 30,000 Americans die every year just from accidents. And if you can read the article, the last line says that it's the leading cause of death for Americans under 35. So as far as the youth of the country is concerned, the leading cause of death is actually accidents. Again, to give you the numbers, about 40,000 people die in road crashes every year, and about 2.4 million people are injured. Now, the map you see is actually a map of Tennessee, and each blue dot is an accident that has happened in the last 5 years. So essentially, the entire road network has had accidents. Okay, the black areas you see are probably black because you don't have any roads. Okay, it's either a national park or something, but the green dots are all accidents, and it's pretty much everywhere throughout the state. Okay, now why is this happening? Now, there are a lot of reasons why crimes and accidents happen. We specifically we are specifically interested in the areas that concern computer scientists and artificial intelligence. And one of the leading issues of crimes happening and ambulances not being able to reach on time when accidents happen is that we have a scarcity of resources. There's only so much, as I showed you before, there's only so many police patrols, and there are only so many ambulances that respond to these emergencies. There's also a real lack of principal dispatch algorithms in the field. There has been a lot of research in how to dispatch emergency responders, but when you go and talk to police or when you go and talk to first responders, it turns out that their approaches are rather myopic. Further, there's also a real lack of principal prediction approaches. So it's if you look at the research community, there has been a lot of research on how to forecast these incidents, but not a lot of them have made it to practice. And finally, criminals and attackers are smart, okay, which means that you can learn a model of crime occurrence and you can place police, but criminals get to observe that and they shift their behavior. So you really have to account for these changes. So for the rest of the talk, this is the problem scenario that we'll deal with. Imagine that you have a spatial area of concern, and you have what we call a bunch of depots or stations. Think about these as parking lots or fire stations for ambulances. You have a bunch of ambulances out in the field and out in the stations. Whenever an accident happens, you also have a bunch of police cars. Whenever an accident happens, your goal is to send an ambulance to the site of the accident. If a crime happens, your goal is to send a police car to the site of the crime. Okay? So the first thing that we did was we broke down the problem into a bunch of modular problems that we've looked at. A lot of them I looked at when I was at Vanderbilt, and we are looking at a few problems at the Stanford Intelligence Systems Lab now. So we want to predict incidents in space and time. In order to do anything about this problem, we want to know where incidents happen and when they happen. Once we've done that, we want to allocate these depots, and we want to allocate the distribution of the responders in these depots. Once incidents happen, we want to dynamically dispatch responders. We want to do this in an online manner, in the sense that as and when information comes in, we want to optimize our policy. Finally, we want to account for robustness in forecasting methods, and then we want to ask the right questions about emergency response, and I'll tell you more in detail about what that means. We have had a few publications for this. We've also been recognized at a few places. We recently won the Innovation of the Month award at the Government Technology magazine. Our work was showcased at the NIST Global City Teams Challenge. And my thesis won a Best Paper award at the AI for Social Good workshop at ICLR. Okay, before we begin, I feel that one of the crucial reasons why our research is a little different than what other people have done is that in the community, you would typically see incident prediction and resource optimization done independently, which means that there's a group that works on resource optimization, but doesn't really take into account how incident prediction approaches would fit seamlessly into their model, and vice versa. What we've tried to do is create this pipeline in collaboration with government agencies that can do both, and I think that's one of the reasons why, to some extent, our approach has made it to the field. Okay, so the first problem that we are going to talk about is how can we predict incidents. I'll not go into the exact technical approaches. I'll briefly go into them. If you have more questions, feel free to stop me and ask me questions. I'll also take questions at the end. Okay, so there's this really famous quote in the community by Jeff Brantingham, who's one of the pioneers of incident prediction. And he said that there was this widespread belief that it's very difficult to predict crimes and accidents. But it turns out that it's not. Ultimately, all we want to do is study these historical patterns, and we want to study covariates that affect crimes and accidents, and we want to create mathematical models for predicting these incidents. So the way we frame this problem is that we have this bunch of historical data where incidents happen at a particular space and at a particular time with some reported severity. Okay? Our model looks at discrete space, which means that we discretize space into a bunch of equally sized grids, and we look at continuous time models. What we also want to do is that we want to capture the effect of a bunch of arbitrary covariates. So for example, how does weather affect crime? So for example, in Nashville, we found that when it snows, burglars try to stick to areas that are very close to highway exits, because highways are salted. They really don't want to get into the interiors of the city, for example. We also want to capture the effect of covariates like the presence of a homeless shelter, say, or the presence of a liquor store in the area, and how does that affect the occurrence of crimes and also accidents. So the way we do that is we use something called survival analysis. Now, this is a rather old set of statistical techniques that was developed in the area of medicine, where doctors wanted to understand the risk or the time to death of patients. What we do is that we transport this into incident prediction by considering regions as lives. Okay? So every time an incident happens, we imagine that that particular region dies, so to speak. Now, there are obviously a bunch of technical intricacies, and I can answer more about that. But it's a fairly straightforward model. You have a likelihood model that you can maximize by standard gradient-based approaches to learn a bunch of parameters. What's really neat is that you can seamlessly fit these bunch of covariates very naturally into the model. So you can throw in whatever you like, and the model will tell you if that has a correlated effect on incident occurrence or not. So, briefly, this is the set of features that we used. For predicting crimes, we looked at a bunch of risk terrain modeling features: population density, household income, household density. We looked at all pawn shops in the area of metropolitan Nashville. We collected data for all homeless shelters and so on and so forth. We looked at how time of day, weekend, weekday, how seasons affect crimes, how police presence affect crimes, and so on. For predicting accidents, we looked at the number of intersections. We also looked at weather, and we looked at, obviously, spatial correlation prediction with varying times. So for example, if a particular region has had a lot of crimes before, what are the chances of it having crimes in the future? And the same with accidents. Okay, so I'll briefly show you some results. These are comparisons with sort of state-of-the-art approaches in the field. The first graph that you see is with an approach, a spatial model called CrimeStab that came out of the NIJ. And you see that our model consistently outperforms their model. The second one is a game theoretic model that came out of USC. And what you essentially see is that we do almost always do better than them. In most cases, we do at least, in all cases, we do at least as good. What's really crucial is the graph at the bottom. Given that our performance is on par, or at least in most of the cases better, the runtime, this is the training time that we take to learn our model, is remarkably low. So you don't even see the bar for our method there. Now, the reason why this is important is because these prediction approaches actually fit into planning approaches, real-time planning approaches, which get deployed in the field. So if you're taking a lot of time in learning your predictive model, that really harms your planning approach and deployment of ambulances and police cars. Now, there are a bunch of extensions, as I spoke. Since then, we have developed a way of doing this online, so we can work with streaming data sets and update our prediction approaches. Also, you can imagine that not all accidents are the same, not all crimes are the same. It's really important that you are able to gauge the severity of incidents. So we have approaches to predict severity in advance. Plus, we have algorithmic ideas of balancing the spatial heterogeneity of your model and model variance. So this is work that I did at Vanderbilt. I want to give you an idea of what I'm doing now. What is really crucial is, as far as crime prediction goes, is that you need to account for behavioral shifts in criminals. So for example, you can place police patrols, but then criminals get to observe those police patrols and they shift their behavior. Okay? So that's why we need robustness. And the way we model it is that imagine, as I said, imagine you have a bunch of grids, you had 3 incidents in those grids, and you placed police in those 3 grids, and then crime shifts to a different grid. So you want to have a model that can systematically and in a principled way learn about these shifts. Okay? So the way we model this is we use this field of learning called adversarial machine learning, in which imagine that you have a bunch of data and you want to learn from that data, but now you have somebody who wants to prevent you from learning from that data. Okay? So this is typically modeled as a game. And when I say a game, I mean game in an economic sense, a game in between a learner and a data generator. Okay? And it's called the Stackelberg game in the sense that it's a leader-follower model where you have to commit to a strategy first, you being the defender. The attackers get to observe that model and then get to shift. And the idea is for you to be prepared for those shifts. Okay? So we came up with a fairly, I didn't want to show too much math, but we came up with a fairly general approach that works with most kinds of incident prediction approaches. So our algorithm is, we just confirm that it works with survival models, it works with logistic regression, it works with Poisson regression. So you can frame take any incident prediction approach, frame it into, sort of have an optimization problem for that, and our algorithm will tell you how to come up with sort of a robust incident prediction model using the Stackelberg game. We have 2 methods of dealing with that. We can directly solve the game, and we have an algorithm to do that, but that's slow. And we also have sort of a faster algorithm that trades off accuracy for speed, which is more of a gradient-based approach, but we embed adversarial learning directly into gradient descent or ascent. So I have a few results for that as well. We have runtime comparisons. And we have results on crime data. So essentially, these are negative likelihood plots. So the lower, the better. What you see is if you use our slower approach, you always get better results. But you can use the faster approach and trade off a little bit of accuracy, but gain a lot of computational speed. Okay. So that covers my work on incident prediction to a huge extent. The next problem that I wanted to discuss is how can we, once we have this incident prediction approach, it's only useful if you can allocate responders and if you can dispatch responders to these incidents as fast as possible. So I did a bunch of work about this at Vanderbilt. a few key highlights are that the allocation problems and the allocation needs drastically vary according to the problem type. So for example, with police and ambulances, the real tricky thing about police is that you can place police, but that affects the distribution of crimes. So you learn a model, you deploy police, but then the model that you've learned changes once you deploy police. That's not the case with ambulances. You can deploy as many ambulances as you want. It's extremely likely that you'll not alter the rate of accidents just because you've placed ambulances. So these are very different problems. For allocating police, we have this two-stage optimization problem where we first allocate police and then responders observe where crimes happen, and in the second stage, they respond. With ambulances, it's slightly difficult. There are a lot of time-critical situations and guarantees that they need to make. So for example, you have to commit that most accidents would be met with, say, a 5-minute latency or a 10-minute latency. So you have to give those guarantees on response time. So we have a bunch of algorithms and some decision theoretic models that take care of that. However, what we have seen, and we've collaborated with the Nashville Fire Department, we've collaborated with the Memphis Fire Department, and we've learned a few key things. What we've learned is that there are a lot of good approaches in research that almost always do better than the approaches in the field. However, when you go and talk to first responders, almost none of them are ready to take these approaches and deploy them in the field. And one of the reasons is that most computer scientists can agree here and figure it out fairly easily that myopic, greedy approaches are rarely optimal, in the sense that if an incident happens and you dispatch the closest responder, you do the best that you can in that situation, but in the long run, you're losing a lot. Okay? However, nobody wants it on their conscience. If an accident happens and you get a call, it's very hard for you to say or judge that, okay, I'm not going to send my closest responder now in anticipation of getting future gains later. Okay? So this is one of the reasons why we figured that there's this huge gap. Even the most simple principled approach will give you better performance than greedy algorithms, but then those will never make it to practice. So what I'm doing now at Stanford is that we are really trying to focus on whether these principled decisions can be made between incidents and not after incidents happen. So once an incident happens, you dispatch the closest responder, but ambulances sit idle at some point. And can you really make these decisions when the ambulance is sitting idle or when one ambulance is sitting idle? So for example, can you use your incident prediction approach and tell that ambulance to go and wait at a better place, so to speak? The other issue with emergency response is that a lot of the times these responders work in situations where communication to the central authorities break down. So for example, imagine a flood or a disaster situation, and you have a bunch of responders responding to incidents all across the city. But oftentimes, it's really hard to understand where they are exactly located, and oftentimes it's very hard to give them exact actions or decisions. So can these agents actually decide for themselves with minimum communication to a central authority about where to navigate? Okay. Now, the way we are tackling this problem is that we are using something called distributed cooperative multi-agent planning. So each agent builds a Monte Carlo search tree, if you're familiar with that, and tries to take the best action that's possible for them. Now, why is this tricky? Now, this is tricky because once you are taking your own actions, you have to account for what other agents are doing. Think of this in terms of ambulances and emergency response. There could be two ambulances who decide to respond to the same incident, okay, which is still fine, but there could be two ambulances who decide to leave an incident for the other ambulance and decide that, oh, maybe the other agent is going to respond to that, and the other agent thinks, oh, no, the other agent is going to respond to that, okay? So there's a very high cost for incorrect estimations. Now, a very simple answer to this would be to just have sophisticated models for predicting what other agents would do. But if you know something about Monte Carlo search, you would need those estimations at every step of the tree. So you also need something that is computationally very cheap, but you also need something that is fairly accurate. So part of my current research focuses on how to build such models and how to do cooperative planning in a distributed way, which involves a set of agents working to achieve a global goal. Uh, Before I finish, I wanted to briefly talk about our approaches, our efforts to make the research available in the field. We have an open source tool, which is currently being used by, well, both the Nashville Police Department and the Nashville Fire Department. So you can just download this tool off of the internet, well, talk to us a little bit and we'll help you set it up. And you can do real-time incident forecasting. You can get analytics on where incidents happen, what incidents happen, which is the area that has the most severe incidents, and so on and so forth. You can also do resource optimization. So for example, a lot of the times ambulances rent temporary parking spots where they're stationed. If you want to re-rent one spot, or if you want to give up one spot, you can use our tool to figure out what's the best area to rent parking spots. Or if you want to change a whole station, or imagine that you want to move 2 responders from one station to another station. What station should you move them to? What station should you pick them from? This tool will help you decide. And finally, we also have a real-time dispatch guidance. So for example, as soon as incidents happen, you can log into our tool and we'll tell you which responder to dispatch so that it maximizes your long-term gains. This is, when I say that this is live in Nashville, I mean, obviously there are a lot of legal constraints. They cannot use a tool to dispatch ambulances or police vehicles. A lot of it is done by 911. But they do use our service as guidance. I have to thank a bunch of people. Well, thanks to CARS and Stanford for having me here give this talk. I have a lot of collaborators from Vanderbilt. We work with a bunch of people from Harvard, and well, with a lot of bodies from the Nashville government. Yeah, that's about it. I will take questions.
Hi. So one thing that came up to your talk is you mentioned some, you presented some potential problems, but there was one thing that I didn't really see mentioned. I definitely like the idea of the predictive data being used to help as it relates to emergencies, as it relates to, say, health. But when you start talking about policing, then, you run into the issue of that data being used to likely victimize people who actually don't get properly served by law enforcement.
Yep.
So how do you kind of approach that and that, and kind of prevent that information from being used to do
Sure.
that?
Yeah. Well, so there are 2 answers to this, or two perspectives to this. The first is the algorithmic perspective. Okay, I think that you can divide crime prediction models into 2 broad categories: one that model environments and one that model people. I do agree that the one that model people, if you give, and models like these have been used before. So you have one particular person and you have his history or her history, and looking at the history, you want to predict whether he or she is likely to have committed a crime. I think that is very dangerous. This is slightly less dangerous because what you're trying to do is trying to pick up environmental factors that predict crimes. And the other thing is that so far, this model has only been used to make sure that once a call comes, a police car reaches there as fast as possible. Which is not to say that, this won't be used in other situations, but we have been very careful about wording our approach and the risks associated with this, with at least the Nashville police. The other answer is more of the policy perspective. If any researcher working with predictive policing tells you that he has developed a tool that will solve the problems of using data for policing or other problems associated with policing, then he would be lying. This is just one cog in the wheel. There is so many other things to do. For example, in Nashville, it was found out, marijuana is illegal in Tennessee, and it was found out that when somebody is caught in possession, the treatment given often varies according to the area of the city where they were found in. If you have implicit biases like that, you can take any predictive policing approach and it's not going to solve any problems. So there is a lot of training that needs to be done. Community policing is a big part of it. But as far as getting help to people as soon as possible is concerned, I think predictive incident forecasting has a huge role to play. Yeah.
About a year ago, I was looking into the response time to automobile accidents, and found, I think your data is probably similar, that most urban areas with highly trained personnel, it's around 4 minutes from the time a call comes in.
Yeah.
The problem that I discovered, though, was communication. From the time an accident happens till the incident gets reported to the correct dispatch center can be 10 minutes or more. And during that time, a person, if it's a heart condition, a really dangerous accident, that's more mortality rate. What happens is people are in shock at first. There's some time for someone to actually report the incident. Then they get interviewed by the 911 dispatcher, who has to try to elicit this information, and then figure out which is the right dispatch center to send that call to. And then the conversation continues. And a little bit of that has been optimized in there, but by the time all that happens, which is all manual, you've spent 10 to 15 minutes.
Sure. I think that a lot of it depends on the area you're looking at. So pretty much all of Nashville and Davidson County, in which Nashville is served by what is known as CAD, which is computer-aided dispatch. So once a call comes in, and this is mostly based on conversations that we've had with first responders. Once a call comes in, it takes them about 5 to 10 seconds to dispatch an ambulance, if an ambulance is available, which is fair, okay? And this includes the human latency of the person who's sitting there. So the CAD system recommending who to dispatch and the human dispatching it takes about 5 to 10 seconds, which is why it's very hard for us to come up with decision-making algorithms at dispatch time, because that's the window that you have. Anything more than that, and first responders say, well, we already have a system that takes less time. Yours might be optimal in the long run. We don't want to use it. Okay? As far as time that takes for somebody to make the call is concerned, I really don't have a good answer about how to improve that. Yeah. I'm sure well, I'm not sure, but I hope it's an active area of research. But my work at the moment doesn't concern with it.
Ayan, I have a quick question for you. When it comes to accidents, the road network probably plays some factor. And as you know, the road network is not something static. It's constantly being reshaped and repaved and rebuilt. Are you able to take that into account in your models?
Oh, yes. So a lot of our current work actually uses real-time traffic routers. So for example, a very natural problem that you can think is, a lot of the times the closest ambulance is dispatched. Okay? Now imagine that on a highway, the accident happened on a lane that goes this way, and the ambulance was going the other way on a different lane. So he has to at least go to the nearest exit. Okay? If you don't have, or that specific road network might have a lot of traffic. Okay? And while ambulances can typically disregard traffic and get a free pass, if it's a choked road network, they can't. Okay, so one of the problems that we saw was using the shortest Euclidean distance is a really bad idea. So we actually came up with real-time traffic predictive models based on neural networks, and now we use those models to find out which the closest responder is, closest not only in space but also in time. Yeah.
All right, Ayan, I think we're out of time, but thank you so much.
Thank you.